Good morning. Happy Thursday. We are moving forward here. We've got just a few things we're going to talk about in the way of fission and fusion today. And so we'll get going with that. What I'm going to do is I'm going to go through, mostly it's going to fall on a PowerPoint. We're going to talk about how the process of fission and fusion. We're going to talk about just kind of the concept of it and then the math of it and where the energy comes from and how those pieces work. So that's the plan. This upcoming week is focused on fission and fusion. We'll be doing some, we're taking the idea of binding energy. That's kind of how that energy is going to be released. And so then when you're changing the nucleus in there, energy is released in that process. And with that energy being released, then we're able to harness that and get the things that we need. So I'm going to share my screen with you. Here. All right, and go here. Maybe, got it. So we'll talk about just sort of the overall pieces and kind of what goes along with this. So hopefully you can see this okay. Make it big. There we go. So we have fission and fusion, and we talked on this graph just a little bit about the way that where they fall on the graph and a little bit about the process of what's happening. But what we have here, fission means to split up. And so when we're talking about fission, we're splitting up the nucleus, which just with that idea alone is a concept that is, I don't know, like thinking about the way that scientists got to that, like, you know what? Let's try this. Let's just see what we can do here, and kind of where they were able to go with that. So if you have a nucleus with more than 200 nucleons, you can split it in half. And so when you do that, the fragments that we call them the daughter nuclei have a higher binding energy per nucleon than the parent, but there's also particles released that some of the energy is released with those as well. And so with both of those, you have it becomes more stable, and there's energy released in the process. So we have both of these things that are happening here. And so that happens if you look at the graph that's on there, it's labeled in the areas that you can have fission. You have to have a large nucleus in order to do that. And so that large nucleus, when it gets bombarded, we'll talk about the process of that in a little bit. It is able to split, and in the process of the splitting, there are other particles that are going to be released. The process looks like this. First of all, spontaneous fission is very, very rare. Naturally found uranium is the largest nucleus. We know that there's other elements in the periodic table. Those have all been synthetic by bombarding the uranium nucleus with a proton and binding it to that uranium nucleus. Now it has another proton, and because it has another proton, it is it's its own element. Many of those elements that have been created are only created for a brief time. They don't continue generating or anything like that. They're created in a lab with the purpose of, sometimes just the purpose of we did it. Sometimes with the purpose of seeing what the characteristics are and if it's helpful in something, but most of the time it's just to have it and know that we can. So isotopes will, sometimes it's isotopes of uranium will fission, but what we normally have is we bombard the nucleus with neutrons, and that will trigger the fission reaction. So if you look at the nuclear equation that's here, you have uranium-235. It's bombarded with a neutron. It briefly forms U-236, and then splits to barium-141, krypton-92, and releases 3 neutrons and some energy. So if you look at the bottom diagram, I want to talk about what's going on here. And this process becomes important because you have to have a large nucleus for this in order for this to happen. So you bombard your uranium nucleus with a neutron. Think about just collisions in general. By doing that, you have this ball for this kind of spherical mass of your nucleus of your uranium. If you come and hit it really hard, it's not going to maintain that same shape. And where you hit it, it'll elongate. Well, at this point, we have to think about our forces. We have two different forces in play in the nucleus. We have our strong force that only responds within a teeny tiny space, so 10 to the negative 15th meters. And then we also have our Coulomb force, the charges. And so when the neutron bombards the nucleus of the uranium atom, it spreads out, it kind of elongates that nucleus. And what happens is the two ends are no longer close enough to experience the strong force. And so because they're far enough apart that the strong force isn't holding them together, the only force that's present between the two ends is your Coulomb force. So now on this end, you have a positive charge. On this end, you have a positive charge, and those positive charges repel. So because it elongates, it doesn't have the ability to and the strength to be held together by the strong force as a whole from end to end. Those ends are no longer experiencing that against each other. Then it's just the Coulomb force, and those positives then repel. When those positives repel, they're each going to naturally form their own nucleus. In the situation here, it's barium-141 and krypton-92. Whatever neutrons are not bound into one of those nuclei, those neutrons are released. And so even though you're going up as nucleons, the mega electron volts per nucleon in your nucleus, so you're increasing where you are on that graph, because there's particles, usually 2 or 3, that are released, they're not included in that. They take energy with them, and that's the energy that we're harnessing when we're talking about nuclear fission. And so it's that interaction, it's the bombardment, and that momentum that's going in there, the way that just naturally is going to shift the shape of the nucleus. And because of that shift in shape, you have enough of a distance between both sides that the strong force isn't holding both sides together. It's still binding protons and neutrons together, but as a whole, it can't hold the whole nucleus together anymore, which then turns it over to the Coulomb force, which is just the positive and positive. Those repel, and they send off in the two new nuclei. And so as a written equation, it looks like what's in that yellow band. As a kind of a picture of what's going on, it is what you're looking at in the diagram below. And so when we're talking about the fission process, you can see that you have those, let's say in this one, you have 3 neutrons that are released. Well, then those 3 neutrons go on to bombard. They have a really high energy with them. So those 3 neutrons go on to bombard each of those its own nucleus. And so what happens is this is where you have your exponential growth here. And so uncontrolled, this is where you have a nuclear meltdown. This is where you have nuclear weapons, where they start the reaction. Every time it releases 3, then each one of those release 3, and each one of those release 3. And so when you have this huge amount of energy that's being released as a whole, you just think about exponential growth, and very, very, very quickly we're getting large amounts of energy. And so that's where the concern is about nuclear energy. Nuclear energy, you can get a lot of energy from it for a pretty small mass of what you need. However, if uncontrolled, then it starts to do this really, really quickly, releases huge amounts of energy with that radiation, and then that's when you have a big situation. So this part here, I just went back a slide, goes through and just talks about what I was explaining in the way that it splits. The bottom line here says that fission of a uranium nucleus gives out about 200 mega electron volts of energy. And so that's just for a single nucleus. It doesn't take that many, like the mass of uranium that's needed to create a lot of energy is immensely smaller than the mass of coal or oil or natural gas. And so the desire is, it's like, well, you can transport that a whole lot easier. You can, you just don't need as much of it in general, and you can get its energy density. We'll talk about that in topic 8, but it's an energy dense fuel with some side effects and drawbacks. And so that's what we have to think of in the way of fission. Fission will always be releasing some radiation with that, and so even when it's all used up, nobody wants to. If they're like, hey, you know what? Let's we could probably just put a nuclear waste spot somewhere, by your house. People are like, whoa, time out, no. So there's ways of figuring out, nobody wants that. So there's a lot of different things that are kind of happening with that. We'll talk about that a little bit more later. Fusion, on the other hand, means joining together. And so if you have a fusion reaction, you have two smaller nuclei that are joining together to make a heavier nucleus. And what happens with this is you have these two smaller ones. They join together. It's usually a multi-step process, and each step along the way requires or gives off some energy. And so fusion gives off more energy per kilogram, And what it does is you have a big jump in there, and just by having fewer nucleons to start, when you release one nucleon and the energy that goes with that, you're still, even though you're going up on the graph there, and you have more energy per nucleon in that final nucleus, you've released particles along the way, and those take energy with them. And because it's not that much energy, there's not that many nucleons, by releasing one, it takes a good percentage of that energy with it. And so fusion gives out more energy per nucleon involved than fission. So fusion gives more energy than fission does. Fusion is what powers the stars. If you look at the second point here, it says each second in our sun, more than 560 million tons of hydrogen fused together to make helium. And one series of reactions, there's different ones, but they all follow something similar to this. You have two separate hydrogens coming together to make a heavy hydrogen that's not very stable and release a beta particle and some gamma rays and then energy. And then, sorry, not gamma rays, neutrino there. So it's a beta particle, so that's your anti-electron. So it's a regular neutrino that's emitted there. And then that heavy hydrogen combines with a regular hydrogen to get helium-3. There's our gamma and energy. And then two of those helium-3s are released or are combined to make helium, which is stable, and two hydrogens. So you're back to having hydrogens, and you can start over. So it recycles the process as you continue through. Each time you have some energy being released. You do have some radiation that's released, but for the most part, it's a small amount. And you don't have the same amount in the way of nuclear waste. You don't have radioactive materials being formed. If we go back here to barium-141 and krypton-92, those both end up being radioactive substances. And so those will experience radioactive decay over time. So even when you have those in the end and you go and put them out as waste, then they continue to decay. And so you have this radioactive material that nobody wants to be by. In the end of fusion, you have helium and hydrogen. It doesn't matter. And so the problem is that fusion is really, really high energy, to the point that even if we could produce the surroundings in order to make it happen, we don't have the capability to actually contain that amount of heat and energy to use it. And so, and I'll talk about that a little bit more in a minute. So here's what this visually looks like. If you look at the top, if you have this process is all kind of happening simultaneously. If you look at the top along the left-hand side, you have two red spheres there. And so you have, each of those is a proton. So those two protons come together. They collide. You release, a positron is released as well as a neutrino. And then you have a red and a gray connected below that. The red is the proton, the gray is the neutron. Remember that when you release that positron, you're going from a proton to a neutron. It's actually changing form. That is your hydrogen 2. Then you have another proton that comes in. Those two bind, releases some energy in the way of gamma. And now you have your helium 3, where you have two protons and a neutron to get those 3 nucleons. That's happening simultaneously with 2 other protons. Then they join together to get the helium, or the heavy hydrogen, the hydrogen 2. Another one comes in, you have your helium 3. When you have 2 helium 3s, those two collide. They make that stable helium 4 and release 2 hydrogens. And those 2 hydrogens can go on to go and do this again. So we get a large amount of energy that's happening here. Again, it's what fuels the stars. And there isn't a clean and easy and straightforward and efficient way to get it to happen here on Earth. So the energy released is radiated by the sun of a rate of 3.9 times 10 to the 20th megawatts. And so when we talk in topic 8 about our energy supply, we'll look at the ability. So with this much energy that's being released, how can we take some of that and harness it in a way that is manageable and useful and cost effective and all of that. However, we want to be able to figure out how we can reproduce this on Earth. So instead of having to just use what the sun is, the small portion of what the sun is radiating that we collect here, that we could actually create this and be able to get it to happen. And so scientists are always working to do that. They talk about the idea of cold fusion. Cold fusion isn't actually cold. It's just at a temperature that we can contain. And so that's what they're working on in doing that. Fusion has a lot of advantages over fission. We have a greater power output per kilogram. The materials don't need to be mined. Hydrogen and helium are naturally found, and we can, like, around us. And so we can take that and use it. There's no radioactive elements that are directly produced from this. And then it means that even with this, that they have a really short half-life, and so they don't need to be stored for much time, and they can be contained safely and then actually disposed of completely. So that it's not just like holding it while it slowly decays over time. Can't use it because they have yet. So the Joint European Torus Project, I'll show you a picture of that in a minute, set up to carry out research into fusion power. I love these these places that focus specifically on these like cutting edge pieces of physics. So, talking about like CERN in Europe, being able to look at the different work that they're doing and figuring out what's happening inside of your particles, thinking about what we have here, where they're working specifically on fusion. And just even the physical setups that are required to get even close to any of this, just the ingenuity that goes into that is mind-blowing. The thing is, it has yet to generate a self-sustaining fusion reaction. It's all about the way that the surrounding requirements needed in order to make this happen. The main problem is getting those two nuclei close enough and for long enough for them to fuse. And the enormous temperatures and pressures of the sun's core provide the right conditions. So for us to reproduce those conditions is just not with what we have the ability to do. On Earth, so conditions that we have around us, temperatures over 100 million Kelvin are needed. And so at this temperature, all matter exists as an ionized gas or plasma. So we don't have the ability to contain this, to have anything. We can't just be like, yeah, I have this super strong container that I'm going to have some fusion happening in. It's not going to happen. We can't, the matter required to do that isn't possible. And so at this point, and so these are the things that they're looking into and trying to figure out in order to solve, because again, if we can figure this out and move forward with some of this, then we're able to take and have it and be able to use this in a way that is functional and be able to get the energy from it. And so, I mean, just think about it. Like you have a fusion car and all it does is pull in some air because it has some hydrogen in it and sets up the, there's a little compartment that allows for the fusion and they have a way to control it. And it just like sucks in some air and creates some fusion and propels your car forward. And it's like, well, that's cool. Buy my car and that's it. I don't have to fill up on it. So I mean, the idea is there, that your house pulls in some air and is able to fuse it and be able to get that energy. So like the ideal energy, the idea of it is really neat to consider. The physical constraints that are making it impossible is what they're trying to figure out. And maybe someday. Containment is, so the jet uses magnetic fields in a donut-shaped chamber called a torus to keep the plasma away from the container walls. And so even with that, it still gets hot. It's just not actually in contact with the walls. And so it allows it to not destroy it immediately. And then in order to get those high temperatures and those high magnetic fields, it takes more energy than the fusion reaction produces. And so at this point, even if they can get it to work, one, it's not self-sustaining. They have to create it every time. And two, the amount of energy required to create that reaction is so much higher than the amount of energy released. So really at this point, all of the research is to figure out what might be possible as opposed to figure out like how to actually use it in a way that is productive. And again, we talk about like the cycle of science and we observe and we figure out, and then we learn how to predict. And then after that, we figure out how to control. So we've observed what happens with fusion. We can predict what can happen, but then actually being able to control it and use it to our benefit, we're not to that point yet. So it's just sort of a neat thing to think about in the way that all of this goes. I want to go back to a couple of these reactions here. And so I'm going to go ahead and do this one. I'm just going to write it on my paper here, and then I'll switch over to what we can see here. So we have hydrogen 2 and hydrogen 3. And we're going to helium 4. So a stable helium with a neutron released and energy. So I'm going to go out of here, go back to this screen. And click on this. There we go. And so we have this. So we can go and we can look at the process that we've used in the other, when we're talking about binding energy. That same process is that we'll go through is what's going on here. So we have hydrogen 2. And if I take the mass of hydrogen 2, it's deuterium. And so I have 2.014102 units. And if I look at tritium, hydrogen 3, I have 3.016049 units here. And then helium, my helium 4, I have 4.00 2602 units. For my neutron, I have 1.008665 units, and then energy. And so we're still looking at this same process of how we do things in the way of adding these up. So if I take and I add these two numbers up, I have 2.014 102 plus 3.016 049, and I get over here, I get 5.030151. When I go over here to the helium, I have 4.002602 plus 1.008665 for my neutron. I get 5.011267. And so I have a mass defect here. Again, these are the parts, these are the whole. And with this, the parts over here do not equal the parts over here, even though two different parts, but they've shifted. And so that's our mass. We can get our mass defect by subtracting this. So 5.0301 or 0151 minus the second one that we have, and that gives us 0.018884 units. So when you have this fusion reaction here, you get your deuterium and tritium, and you get helium with the neutron. You have a mass defect on that of this point, this is a zero, sorry, terrible zero, 0.018884 units. We can take that number times 931.5 mega electron volts. And when we do that, we get 17.59 mega electron volts. And so if you're just looking at that single part of that reaction, you have that much energy that's released. Many times on these reactions, I just did the single one. If you have other ones and you're looking at kind of the chain of that, you have some energy that's released each time. And so based on just a couple of atoms that are coming together, going through that quickly, you have a lot of energy that can be released. The other thing I want to look at, if we go back to this, actually, we're 9:35. I'm going to go ahead and wrap up. We won't be able to get through that whole one. The other one that I was just going to do was to go through and do a fission reaction. And so I'll look at that briefly and just talk it through, just to make sure that you have the idea of it. We go back here to our fission reaction that we used as an example. When you have your U-235 and your neutron, that U-236 is just a very, very, very brief moment that exists, but then it splits. And so if you take your mass of your uranium atom and the mass of your neutron, you don't need to do that middle split there, but that transitional U-236. But then if you look at barium 141, krypton 92, and your three neutrons, if you take the masses of those, again, in the same way, you would have that mass defect. So similar to what we just did with the two hydrogens. And so because of that mass defect, if you add the parts of the uranium and the neutron, and then add the different parts of your barium, krypton, and your neutrons, there's a mass defect there. That mass defect is energy that's released into the surroundings. And so both of those pieces are working together to create what we have. So things that you will be looking at this week, I'll get this posted up today. You'll have some practice problems. You'll have a simulation that you're working with and doing some different things. Just, it's not anything that's super fancy. It's just like being able to see and experience what's happening, sort of visualize what's going on with that. And then you'll have some practice problems that go along with that. I did shift things because we meet on Thursdays, and I wanted to keep it so I was introducing before the weekend, so you could have just a little more time on things. I moved due dates up to Wednesday. If you missed that yesterday, that's fine. Just get it in. It's not a big deal. But that way we'll have things wrapped up, and then on Thursdays we can introduce and move forward. Keep working on your practice. Keep working on your IA. I have several people I'm meeting with on Friday, and then I will put up a couple more times next week if you missed the ability to come through, or if you have other things you need to address with that. March 9th, Tuesday, March 9th is the due date for getting that in. So hopefully hopefully once you have your rough draft meeting, you can move forward and get things wrapped up and be in good shape with that. I'm feeling confident about the conversations we're having, about the places people are at. You guys have gone through this with, a good, you had some stuff that you did before we went distance, but for the most part, a lot of the IA work that you've done has been since you've been at home. So I commend you for the work that you've done in that. It's not an easy thing in general, and it's especially not an easy thing to do in isolation. So really, really nice job. I'm enjoying the things that I'm seeing with what you're doing. So keep up the good work. I'll be on for a couple minutes if you have any other questions. Other than that, have a great day. Get outside and get some of the sunshine. Enjoy your weekend, and I will see you on Tuesday. We'll see you later. Bye-bye.